In this video, we're going to look at the in-class activities, the solutions for parts B and C. So in question 1, we were asked to express the equilibrium constant for the following reaction. So we're looking at P4 combining with oxygen to make phosphorus pentoxide. So we have the phosphorus, which is in the solid state, the oxygen, which is a gas, and the phosphorus pentoxide, which is pure. And if we have anything that's pure, it's not going to show up in the equilibrium constant expression, because remember, equilibrium constant expressions, it has to be part of the system. It has to be able to be expressed as a mixture. So gases or molarities or aqueous. So that's what we're looking for. So when we put our products, so this is our products, but it's pure. So since we're not going to see this one, we're going to leave an understood 1 over our reactants. So the P4, that's pure, so we're not going to worry about it. So we just leave that as 1, multiplied by the concentration of the oxygen raised to the 5th power. So the oxygen to the 5th power. And mathematically, 1 over something raised to a power is equivalent to this right here. So we've got the oxygen raised to the -5th power. So 1 over a number to an exponent is the same thing as that number raised to the negative of that exponent. So this is how we're getting A for the correct answer here. So a couple of things to remember from this question. Pure things don't show up into the equilibrium constant expression, and we need to make sure we understand how to do our exponents. Now in question 2, you're given 2 reactions, and they look kind of similar. And if you'll notice that as we compare this reaction to this reaction, this one's written in the reverse direction. So HD is on this side, HD is on this side. And also too, the second reaction is twice that of the first reaction. So we can use that information to figure out the equilibrium constant for the second reaction. So if we know the first reaction, products over reactants, so the H2 times the D2 over the HD squared, and they told us that that equals 0.28. So if I reverse the direction, then I have to switch. So I have to invert, because now this is my products and this is my reactant. So they switch places. So when I do that, I invert the 0.28. So 1 over the 0.28. And then because we squared it, because we multiplied everything by 2, we doubled the coefficients out in front. So see how we have this raised to the 4th, this raised to 2. So we have to take that 2 and make it an exponent as well. So if we take the original K value, invert it, and square it, we will get 12.755 in the calculator. And if we put it to the correct number of 6 bigs, that'll be 13. So this is how we're getting E for part 2. So if you reverse a reaction, you invert it. And if you double a reaction, or if you multiply a reaction, then you raise that K value to the same exponent. Here we have another similar type of reaction. So we're given these 2 first reactions and their K values, and we're looking for the third K. So as I look at this, I notice that if I add the first 2 equations, I'll get the third equation. So that get the A plus the A, so that's 2A, the B, and the AB's cancel out because I've got 1 on this side, 1 on the other side. And the A2B comes down here. So this K is a result of adding these 2 together. So when we add equations together, we multiply the K values. So the 0.24 times the 3.8. So just to show you why this works, so let's look at the K for the first reaction. So AB over A times B. For the second reaction, that's A2B over AB times A. And if we multiply KC times K2, So we're just multiplying these two together. So the AB's cancel out. A2B is on the top. We've got A times A, so that's A squared, and we've got B, so it reduces down to this. And if we look at writing the equilibrium constant expression from just the reaction, it's A2B over B over A squared. So when I put this in my calculator, when I multiply these two K's together, I get the 0.91. So this 0.91 is the combination of those two reactions. So question 4, we're looking for the delta N for the following reaction. So we're converting the Kc to a Kp. So the equilibrium constant for concentration, so like molarities, to the equilibrium constant for pressure. So there's an equation that helps us to convert between those, and that equation uses delta N. And delta N, so the delta always means final minus initial. It means change. So the change, final minus initial. And then the N means moles, just like when we did the ideal gas law equation, the PV equals nRT, N is still moles. So we're looking for the final moles minus the initial moles. So I look at my equation, I've got 2 moles of gas on this side. I've got 1 mole of gas here, 2 moles of gas here, so a total of 3. So 2 minus 1 gives me -1. So this is where I'm getting a -1 for the delta N for question 4. Now in question 5, they want us to determine the K value, and they've given us the equilibrium constant values. Sorry, they've given us the equilibrium values for the concentrations. So if I'm looking for the K, I'm writing my K expression, so my products, the N2O squared, because I've got to pull out that 2 in front, products over reactants, so the N2 raised to the 2 times the oxygen. So there's our expression. Now we just got to plug in our numbers. So the N2O, so I'm just plugging that in there. The nitrogen concentration is 3.6. The oxygen concentration is 4.1. So I put this in my calculator, and I have to be careful, make sure I square it here and divide, and make sure this, when we divide it by the 3.6, it's 3.6 squared. Also make sure you have enough parentheses in here so that you're following the orders of operation. But if you put this in your calculator correctly, you should be getting 2.0 times 10 to the negative 37. So that's how we're getting D for question 5. Now in 6, we're looking at the following reaction and the equilibrium concentrations. And they've given us the equilibrium constant, but they want to know what is the equilibrium concentration of NO2. So very similar to the previous problem, but we're just looking for a different variable. So I'm still starting off by writing my K expression. So my K products, so the NO2, so it's squared. So there's my products, and then over my reactants, my N2O4. And I'm making sure, yep, that's a gas, that's a gas. So these are partial pressure, those are mixtures, so they're not pure. So I can do this. And they give us the K value, so I'm plugging that in. They've given me the equilibrium value of the N2O4. So I'm plugging that in there. So this is where I'm getting this equation. So the 0.21 equals the NO2 concentration squared over the 0.039. I'm going to multiply both sides by the 0.039. And that's where I'm getting the 0.00819. And because this is squared, I'm going to take the square root of both sides so that I can get just the concentration of the NO2. So the NO2, when I take the square root of the 0.00819, I'm getting 9 times 10 to the minus 2. And so that's how I'm getting A for question 6. So here they're asking us to consider this reaction and they give us a K value. And they're also giving us the concentrations of the mixture. And it doesn't say that it's at equilibrium. So we need to test it out to see where it is. So we're going to set up and calculate the Q. And remember, the Q looks just like the K, but the K means that it's at equilibrium, but the Q is still products over reactants. So here I'm setting up my Q, my products, my CO2, and the copper is pure, so I leave that out. And then the water, it's also gaseous, and this is gaseous, so we're gonna keep it, so the H2O squared. So those are my products divided by reactants. The copper oxide is pure, it's a solid, so we don't include it. And then the CH4, so this is our K expression, so our Q expression, sorry. And now I'm gonna plug in my values. So my methane, the CH4 is 0.22, the CO2 is 0.67, and the water is 1.3. So when I put that in my calculator, the 0.67 times 1.3 squared, all that divided by 0.22, I get a Q of 5.1. So now I'm comparing this Q to my K. The Q is larger. So if the Q is larger, that means I need to get that value smaller. So I need to decrease my Q value to make it match my K to get it to go to equilibrium. So to get it to go to equilibrium, to get that Q smaller, I've got to get rid of some of my products and convert it to reactants, because that's the only thing that's going to make this number smaller. So the product value has to go down, the reactant concentration has to go up to get the Q to a smaller value. And once it gets to the K value, that 1.10, it'll stop because it will have reached equilibrium. So to get to equilibrium, Q needs to decrease, and Q will decrease if we remove products and increase the reactants. So we're going to shift in the direction of the reactants. So that's how we're getting A for question 7. Okay, question 8. So we've got cyclohexane, and it undergoes a molecular rearrangement in the presence of the aluminum trichloride to form methyl cyclopentane, according to this equation here. And they've given us the K, so they've given us the equilibrium constant, and they want us to find the equilibrium concentrations if the initial concentrations are 0.2 and 0.075, and so these corresponds to these concentrations here. So I'm going to start by, I'm not at equilibrium, but I do have the initial concentration. So I'm just going to look to see where I am. So I'm calculating the Q. So I'm putting my products over reactants, and my Q comes out to 0.375. 0.375 is larger than the 0.143. So I'm going to have to go in the reverse direction. I have to switch the reaction so that it goes towards the reactants instead of the products to get that Q down so that it matches the K. So now that I know which way the reaction needs to go, I'm going to set up my RICE table. So my RICE, the R stands for the reaction. So there is the cyclohexane, and there is the products, and they've given us the initial concentrations. So the 0.2 for the cyclohexane and the 0.075 for our other product. And since we said we're going in the reverse direction, I'm going to subtract X from this side because I don't know how much I'm going to need to go in that reverse direction. So I'm going to just subtract X. Now, because this is a 1-to-1 mole ratio, for every 1X that I subtract from here, I'm going to have to add the same amount on this side because it's a 1-to-1 mole ratio. So I have to keep in mind the stoichiometry. So minus X plus X. So again, this is the initial concentration. This is how much it changes, and this is the ending value. So we just add these two lines together to get the ending amount so that when it reaches equilibrium. So now I'm going to set up my K, and they told us that the equilibrium constant is 0.143, and then products over reactants. So our products, 0.075 minus X, and that's understood 1, so that's to the 1 power over the reactants, so the 0.2 plus X. understood 1 here, understood 1 here. So now I'm just multiplying this out. So multiplying the bottom, both sides by the 0.2 plus x, by the 0.2 plus x, and I'm just doing the algebra to isolate x. So I've multiplied both sides by the 0.2 plus x, and then I'm going to isolate it so that I had all the x's on this side. And then I'm going to divide through by the negative 1.43 to isolate the x, and x is 0.04059. Now don't stop just there, because that x is just the change, and they want the equilibrium concentrations. So what I'm going to have to do is plug x into here. So I'm adding x to this side, the 0.2 plus the 0.04, and the 0.075 minus the x to get the 0.034. So this is the concentration of that product at equilibrium, and this is the concentration of our reactant at equilibrium. So I'm matching that up, the 0.241 and the 0.034. So this is how I'm getting C for number 8.